Lucas.
Thank you for the introduction. I'm Lucas. I'm just finishing my PhD at the Federal University of Pernambuco, which is held in Brazil. This work is a result from an internship at Microsoft Research mentored by Ben, David, and Margus. So I would like to start just saying that something should happen. Okay, gestures are everywhere. So right now, as an example, let me show you, just remind you some numbers about Kinect. So on the two versions of the Kinect, we had more than 44 million units sold on early 2016. This is a gesture sensor which is capable of recognizing the user body joints on real time. It also provides color information about the scene, depth information about the scene. And this is how this gesture sensor looks in VR. So here the user is interacting with virtual content using hand gestures. And we also have it applied to augmented reality scenarios. So here, while using a HoloLens, the user can see augmented content on the scene and interact with it also with hand gestures. So these kind of platforms, they are growing, they are appearing. Now we have tons of gesture sensors of all sorts and sizes. They are getting cheaper and getting everywhere. And they also probably will become with application stores. So for example, the Xbox One and the Microsoft 10, Windows 10 has an app store, and this will become the platform for applications while using gestures. So there are some problems to this scenario. The first one that I would like to talk to you about is the privacy. So once the applications want to embed interaction with gestures on their flows, they need to have access to some data from the sensors. And this today is given by providing the application some depth frames, some skeleton frames, and it raises some privacy concern. This is sensitive data. Another problem that we want to tackle is safety. So the gesture recognizer, they can ask you to perform a gesture that may be not safe for you. And also you have conflicts. So the gesture recognizer may ask you to perform a gesture which is also required by the system. So let's say on Kinect you have this attention gesture, which is required by the system, and it should not be overridden by an application. You also have conflicts between two gestures on the same application or different applications. So we would like to avoid this kind of issues. Then we looked around some ways of performing gesture recognition. So this is the naive approach. This code is presented on a white paper of Microsoft Visual Gesture Builder. This is what you do early on the development process to develop a recognizer. So we just build Boolean expressions, and you try to fit these expressions on a particular body posture or gesture. But these have some issues. This may present conflicts, as we told before, so you can write two gestures that are triggered at the same time with this kind of code. You can also have safety issues. You can ask the user to perform impossible postures with this. And once this code grows bigger, it's hard to analyze. So what developers usually do, they run to machine learning approaches. So here, for example, have the wave gesture. On machine learning, what you do, you record variations of this gesture. So you ask users to perform the same gesture. Maybe you want variations about the illumination conditions or the sensor orientation. And for this, you usually need some machine learning knowledge. It's also required a minimum data set size depending on the algorithm. And the recording and tagging this data is almost always expensive on the development process. Editing the gesture is almost impossible on machine learning approach. So let's say I just have a good recognizer for the wave gesture. Now I want to recognize the goodbye gesture, which is up here. I have to do the whole process again. I can't reuse the software or the recognizer that I already have on the previous gesture. The recognition time is not always on real time, so There are some issues still on some machine learning algorithms, and they usually don't give you detailed feedback. What I mean by this is that the machine learning approaches, they usually give you the output once you finish the gesture. They don't give you output continuously while you are performing the gesture. And we wanted to do this on our approach, so we wanted to tell the application in which part of the gesture the user is. And also, it doesn't handle conflicts, as the previous approach also does not. So there are some previous work on this about privacy. Particularly, what they try to do is to limit access to the application, so the applications do not have the whole content about the sensor. The color frames, for example, can be converted on edge images, so you can use some edge filter and just provide fewer information for the application. And you can also just cut off the color frame and send only the depth frame for the application. But then, on the depth frame, you have information about the environment, because you can understand shapes, so you can understand what kind of furniture the person has at home, or what kind of objects they have. Oh, sorry for that. So the other two issues are about the silhouette. So you have also the information about the user, clothing and weight, for example, once you have the silhouette, and the skeletons. But even if you give only the skeletons, you are giving processed information for the application, so they can automatically infer some properties of the user just by analyzing the data. So what we wanted to do is this. We wanted to give a trust boundary between the applications and the sensing data from the user. So here we have the Prepose concept, which is our solution. You have the user on your left, and then you have the sensor sensing the user. It sends the skeleton data to our runtime. And what you do is that you have the applications on the other side, and they don't have access to the skeleton itself. They just request information about the interaction of the user. So they ask if the user is performing a particular motion, or a postural behavior, or a gesture itself, and we return the gesture events. So these requests were Prepose code. So we built a domain-specific language to formally describe gestures, which can be later statically analyzed by Z3, which is a constraint solver by MSR. And here, we just translate the code of Prepose into Z3 expressions, which can be analyzed. And then we have our trust boundary. So how we came up with this? We watched a lot of applications, gesture-based applications. So here, for example, we have a physiotherapy application, which tells the user to raise your left leg to the side and return. So this is a textual description of the gesture. And you also have the number of repetitions that the user should do that. And they also have the feedback in red, telling what the user is doing wrong. So the insight here is that they describe the gesture by text. And we thought on our hypothesis that this may be enough for a machine to recognize the gesture. And it's also, on an HCI point of view, it's also very good for a developer to write gestures on this kind of language, which is natural English language. So we did that. Let's break down the phrase of raise your left leg to the side. There is an action. And then you have the body part relative to that action, and also a direction to that action. So what we did in Prepose is that we built our language, and so you can write a phrase like this: rotate your left elbow 20 degrees to your left. So here we also have an action, we also have a body part, and we have the angle and the direction of the rotation. What happens in runtime is this: we build a function called rotate. Actually, these functions right now, they are very hard-coded, but they can be increased, they can be embedded one function inside another, so we can grow on this. And we grab the information about the left elbow from the data provided by the Kinect sensor and provide the arguments needed for the function. So we have the 20 degrees and the left direction as argument for rotate. So this is an action. We have some actions built in Prepose, and by using those actions, we can build gestures. So let's say the action is a primitive, but we can build poses out of actions and gesture out of poses. So here, for example, we have a ballet gesture, and on this gesture, we have two poses. One pose telling the user how to place the legs and the feet, and the other pose telling the user how to place the arms. And to finish the gesture on Prepose, you have to say how it should be executed. So here, for example, the code is saying that you should first perform the cross legs one behind the other pose, and then you perform the second pose. So what about safety? What we did is that we coded constraints on Z3 that should be safety constraints for the user. So we have a spine constraint that tells that the application is not allowed to ask the user to bend his spine. We have an elbow constraint that tells that the application is not allowed to ask the user to rotate his elbow on the opposite way. So these are generic constraints, but you also can have specific constraints depending on the age of the user, or if the user has some physical disabilities, you can add another constraints for safety, which will tell which kind of gestures the user can perform or cannot to the application. And how we check it is like this. We have the current state of the user body with the positions, and we assume that it is safe right now at the moment that it's captured. Then we go through each step of the gesture and ask Z3 if it's still safe after the execution of the step. And then we go through this. If the gesture is not safe, we can tell the developer which part of the gesture, which particular action of the gesture is not safe. About conflicts, we have a similar approach. So we just send Z3 the two coded gestures with the poses, and ask Z3 if they have conflicts. That means they can be triggered at the same time or no. So we can detect conflicts between the system gestures and the application gestures, between two gestures on the same application, or gestures in different applications. So the main two concerns about evaluation were, is Prepose expressive enough to describe gestures, and is it fast enough to run real time for applications? So these concerns were evaluated. So we built gestures on 3 domain applications, which were physiotherapy, ballet, and tai chi. We have an average of 9 lines of code for each pose. And regarding performance, yes, Prepose is fast enough. It runs at 30 frames per second, which is the top frame rate for the sensor, the Kinect sensor. And the matching time is really fast. It's about 3 milliseconds. And the pose transition, it takes 91 milliseconds. Regarding the submission, so once you write the Prepose code, you want to know if it's safe enough or if it has conflicts. So you don't need to do that on real time, but you can do it once you write the code and submit to the App Store, or let's say you just compile the code and Prepose. So to check for safety, it took less than 1 second, and to check for conflicts, it took less than 1 minute. Okay, so as conclusion, I just show you the Prepose, which is a language to express gestures. And it's also a runtime, so you can try out and see if it recognizes the gestures that you wrote. It supports privacy because it's a trust boundary between the application and the sensor data. It's also able to check for safety and conflicts using Z3. So at the submission of the application, you can see if your gesture is safe and if it has conflicts. And if not, you can know why it's not safe or where is the conflict. So as I told you, I'm just finishing my PhD, but I'm still pursuing this direction. I want to get further on it. So as future work, I intend to add new actions and primitives to improve the expressiveness of Prepose. So right now you can say the user can point to some direction, can rotate the arm to some direction, can put a joint in front on top of another, and align joints, but we want to increase that so we can closer to the actual textual description that you have on real world. We also want to add time constraints, like say you want the user to perform a gesture slowly or fastly. We want to support that on our language. We want to build reusable gestures and provide it as assets on a store, so you can just grab one gesture that on a store, let's say the wave or punch or jump gesture that you have in the store. You can also edit it, unlike you can do on machine learning approach, and develop some example applications so developers can know where to start with. At last, we want to add sensors. So as I told you in the beginning, you had a lot of hand gestures on nowadays VR and AR. We want to add lip motion. It's quite simple. The structure is already there. You have just to add the sensor, lip motion, the interior sense, and others. So we also developed a Prepose Explorer, so you can write Prepose code on this application that we did. Here you have the syntax highlighting and all, and you can try it out just pressing the play button. So you can test it right out. And below you can see the progress bar. So as I told you before, we show in which part of the gesture the user is, and also on the top, on the bottom right corner, you can see the number of completed times that the user completed the gesture. So that's it. I think that the beauty of Prepose is that it aggregates HCI and privacy and security. And you also can download it. It's available on GitHub, and we take pull requests. So thank you for your time, and I'm open to questions.
All right. Questions? Yes, Jaeyeon.
Very interesting work, Jaeyeon Jung, Microsoft Research. So you evaluated the expressiveness of Prepose with those 3 applications, but I think that maybe ultimate kind of challenge is to evaluate yours against like Dance Central. Like there's a lots of sort of dance move. It might be hard to express with your limited vocabulary. So what do you think about that?
That's a good question. And also that's a great case study that we could do. So right now you can write each position of the body with Prepose. It supports all current states of the body. It may be too rigid, so we also implemented like restrictions that relate to joints. So you can, instead of saying do 20 degrees to that direction, you can say just put the hand on top of the other. So we think that it's expressive enough. That's while coding tai chi poses, we saw some things, some postures likewise dance and also in ballet, but ballet is quite rigid. But in tai chi is more like a flow gesture. So I think it's quite good for that case, yeah.
Okay.
Good morning, Peter Neumann here. I missed my tai chi this morning. I had a question as to whether there's any synergy between your work and the Purdue work on interpreting American Sign Language, whether your approach might be useful to them or whether their approach might be useful to you.
Yeah, that's a great question. So usually when they interpret sign language, they use machine learning, and they gather a lot of data, because the signs, they are already there. I mean, they don't create gestures. The gestures are already, they don't create much gestures, at least. The gestures are already there. So I think there's a slight difference. But once you have hand tracking on Prepose, yes, you sure could do that. You could introduce restrictions and transformations on the hand skeleton and understand which gestures are being held. And the description is maybe be good enough for tracking this kind of gestures, yes.
Hello, this is Fish from UC Santa Barbara. This is a piece of awesome work, thank you. So I noticed that you use Z3 for constraint solving. We all know that Z3 is a good tool, but sometimes like when you have a large constraint set, it may take a arbitrary amount of time, and you really don't know how long it's gonna take. Is it okay in your use case?
Yeah, I mean, as I showed you, we did run the check for conflicts and safety, and it was really fine once you do it offline. On the online part, it's really fast. You have 3 milliseconds for matching. Once you the transition between one pose and another. So I was doing a gesture and I transit between two poses. It takes 91 milliseconds, so I think it's fine. We can discuss the details later if you want. I mean, there are some tricky parts.
To know what sort of optimization you need to have.
Yeah, we can talk about it. I think I run out of time, so we can talk about that later. Thank you.